All right, this is another design time-lapse video in SolidWorks for the Ultra4 design. What I'm going to be going over today is the front bulkhead subassembly. So all of these 4130 chromoly plates that captured the shocks for the shock mounts, as well as the design for this upper control arm cross brace, which is made out of billet 7075. It should be a really interesting video showing the iterations that I did on some of these parts and how they fit in the larger assembly and which components they tie into and which components tie to each other, and making sure that all of these parts are able to be fabricated and machined and that they're structurally strong in the right places and not too heavy. Should be an interesting video. And what we're going to start with in the time lapse is the design for this spare tire cage here in the back, which captures the 58-inch Mickey Thompson spare tire with an exhaust port exiting through the center of the wheel, which is fed into by an 8-into-1 header into a 5-inch collector and a 4-inch output pipe. And the idea behind this design is that when you have the car jacked up on stands to change the spare tire with the suspension fully drooped, this spare tire assembly can swing down and contact the ground, and you'll be able to get the spare tire out without having to lift it 4 feet into the air, because this tire by itself, just the rubber on the tire, weighs 230 pounds. And then when you include the 24-inch double bead lock, the whole assembly's probably over 300 pounds. So definitely too heavy for even 2 guys to lift by themselves. And then I have this rear winch back here, which you could loop the cable around into this D-ring to help you start lifting it over this pivot point by applying a lever on this corner here. So that's what we're going to start with first in the time lapse. Talk about some 3D sketches and some weldment features in SolidWorks, which is really good for cage design. And then we'll move on to some sheet metal and billet super cool parts. So for the spare tire carrier, what I need to figure out is how I'm going to design the pivot mechanism for the cage that goes around the spare tire. And I decided to use the same heims that I used on the sway bar. And I need these chromoly weld nuts that are going to tie into the sheet metal. So the advantage of these weld nuts is they're designed for a specific DOM tubing size in chromoly, and you just pop them into the end of a tube, you weld them to the tube, and then you can thread the rod ends into those weld nuts, and then you capture it with a jam nut. So I need to make sure I have that pivot in the right point. The goal is to have the pivot point be on the same plane that the curve on the exhaust starts at, so that when the tire swings out, it follows the arc of the exhaust and doesn't interfere or crash into anything. So you can just have that center hole through the center of the rim go right around the exhaust without touching it, and then it swings out and around that arc defined by those pie cuts, the exhaust tailpipe. So this is a perfect opportunity on a part like this to use 3D sketches, and the advantage to that is you can map out really complex shapes that you would not be able to make using regular features of like bosses and cuts and sweeps. And the other advantage to 3D sketches is that the Weldments tool in SolidWorks is designed to be used with 3D sketches. So you just define a shape in the form of a 3D sketch, and then you select segments of that sketch to define your weldment. And when I say weldment, that means a tube cage. That's what SolidWorks calls their tube cage features. And so what I need to do is have enough clearance on the outside of the cage to capture the spare tire and make sure that it can also fit inside of the cage. And the other cool thing about this design is that when the tire is in its mounted position, the top of the tire has a cage around it. So if the vehicle were to flip, it would just slide along that cage without being hung up on rocks, because the tire is completely encapsulated by the cage. So I just need to make some simple hoops and some simple straight lines here to cradle the tire and to grab those mounting points on the rod ends, and then have a center hoop where the exhaust can flow out of. Then I have cross beams going along the radius of the hoops to capture that center hoop, and then the whole part is going to be really strong. So now that I've defined that sketch, I can start using the Weldments feature in SolidWorks, and that weld nut that I talked about at the beginning is designed for 1.75 inch outside diameter tubing with a 120 wall thickness. So it's really easy to modify the dimensions of your tube profile using the SolidWorks weldment tool. And then you have different groupings of different parts of the sketch to define continuous sweeps of the tube. And 3D sketches can be a little bit finicky if you have too many dimensions constraining them because they're all sort of tied to each other. So I like to work in nodes and keep things straight wherever I can and make sure that everything's defined in all 3 axes. So then these center sections are going to grab that spare tire mounting plate, and these are the main structural members that hold the tire onto the cage. So that looks really good. Just adjusting some clearances here to make sure everything fits. And then I'm going to use another limit mate on this part so that it can be in the fixed position of 45 degrees with respect to the bottom plane of the vehicle. And then it can swing down 270 degrees to be vertical. So now that part can swing everywhere that I need it to swing. It's not going to hit anything. And then when the vehicle's in full droop, when you're changing a tire, that bottom part hits the ground and then the center of the wheel passes through that exhaust. So now I'm checking the dimensions of the tire. According to Mickey Thompson, this 58-inch tire weighs 230 pounds by itself. The model that I had originally estimated was over 300 pounds because I was kind of guessing at wall thicknesses. So I reduced some thicknesses wherever I can. And what you're seeing now is me convincing myself that I do not want to redesign the entire wheel because that wheel weighs 130 pounds as it's modeled because it's way too thick because I don't really know anything about wheel design, but there's people who specialize in that. So now I'm starting on the front bulkhead. What the bulkhead does is it ties all of the front suspension components together. So that includes the lower control arm mounts with those polyurethane bushings. It's going to capture the differential on a plate, and it's going to capture the shock mounts on top. A normal bulkhead would also capture the upper control arms, but for this vehicle, I'm going to make a really crazy billet piece that's going to capture those upper control arms because there's not a ton of stress on the upper control arms anyway, because it's not load bearing. It's just taking a lateral force when the wheel goes over a bump. But the lower control arms and the shocks, that's where most of the force is going to be, especially when you hit a big bump head on. So I want all of those parts to be tied into each other with a chromoly bulkhead. So I'm just counting inches here to make sure I have planes in the right place. And then on those planes, I'm going to make chromoly plates that will capture the lower control arms and tie them to that center diff. And these are really simple features because they can just be flat plate of chromoly, and then they're just going to have a tube running through the center of them, and then the bolts for the lower control arms. So pretty simple boss here. I'm going to mirror that onto the other side and then add my mounting holes. So what I'm doing here is providing a plate for the center beam of the frame to go through. I haven't defined any features on the chassis yet, but what I'm doing is setting a constraint for myself where I know for sure that the bottom of the frame is going to have one big tube running right through the center of it. And that's going to tie everything together in the whole car. And all of these plates are going to mount to those. So now I'm just applying the hardware. I'm using 1-inch diameter grade 8 bolts with castle nuts on the end of them. So the idea is that these would be locked in with a cotter pin, kind of like the swing arm on the bottom of a motorcycle. So you don't have to waste big, giant, expensive 1-inch lock nuts because nylon lock nuts, you're really only supposed to use them once and then you have to throw them away. But for a part like this, you want to be able to take the lower control arms on and off as many times as you need to get the shock tuning correct. That's why those cotter pin castle nuts are the right application for this. So now I've made those bosses for the top shock mounts. Those are just simple slot shapes, a rectangular profile with rounded edges. I need to figure out what type of sleeve bearing I'm going to use for these because, like I mentioned in a previous video, you don't want any load bearing force on the bolts in the shear direction because the bolts are only strong along the direction of their axis, whereas those bearing sleeves are much stronger in shear. So all the force coming through the shock into the bulkhead is going to be absorbed by those bearing sleeves, and then the bolts just serve the function of tying everything together. And then the other advantage to these sleeves is that it reduces the diameter of my through hole. So it allows me the opportunity to use a smaller size bolt, I can use 12-point bolts again, which are my favorite bolt. So I have 12-point screws and lock nuts. And lock nuts are fine here because the top of the shock is never really going to be unbolted from the vehicle unless you're replacing the entire shock. And it looks like everything cycles correctly. So now I can start working on tying in those top shock mounts to that bottom plate on the bulkhead. And I'm going to do that with some simple features in the form of another big plate. I used 1/2-inch thickness chromoly on the bottom plate and the lower control arms, and then I'm using 1/4-inch plate here because there's 2 plates tying everything together. So I'll have the same strength as the bottom, but it'll be spread across 4 parts instead of 2 parts. So another SolidWorks trick here, if you want to make one part file that has multiple part geometries within it, what you do is every time you make a new feature, like a boss, you uncheck the box that says merge result, which is defaulted to be on. And what that allows you to do is have different plates that represent different part cuts in a part file. And then you can put unique features on each body because they're not merged to each other. So you can have 2 pieces in the part file that are touching each other that would normally be merged. Those can be separate, and then I can put chamfers all around them like a real part when you fabricate it. And so what I'm doing here is I'm making one master sketch that I'm going to duplicate 4 times. And I'm making this on the center plane, and then I can convert this sketch entity onto the actual boss planes that I'm going to be using. That way, if I need to make any edits, I only need to edit one master sketch rather than any change that I make. I have to duplicate that change 4 times. So it just saves a ton of time. And I have some structural cuts here, that X shape that you see, to make it light and strong and rigid. And I'm not really sure what this part is going to end up looking like in the long run because right now it looks really tall. I don't think it will be flimsy in the longitudinal direction of the vehicle because it'll be tied into the frame and welded, but I'm thinking about boxing it in to make it extra strong because most of the bulkhead designs that I've seen are boxed pieces of sheet metal that are sometimes complicated. This one's a little bit simple on its first iteration. So now I'm making probably the coolest part on the whole vehicle besides the trailing arm. This is going to be the most prominent piece because you'll always be able to see it. And what it is the upper control arm mounting bracket. So it's going to be a big giant billet 7075 aluminum piece. And the reason I did not want to use sheet here is because those pivot points on the rod ends are at really weird angles with respect to each other. And I need to capture them in a way where sheet metal just wouldn't work for this application. Unless you had really, really precise bends, the whole thing would bind up. So I just decided to use aluminum on this part because the upper control arms have the lowest amount of force on them out of any component in front assembly because there's no shocks attached to them. All they're doing is keeping the wheel upright as it cycles through the suspension. And the only force load that you would get on it is a lateral force load when you're going through a turn. And since those rod ends are spread so far out, their respective moment arms really reduce the force on each. So I'm starting by defining the upper control arm spherical bearing locations, which are all at 30 degrees with respect to each other, but they're slightly offset from the origin. And what I'm going to do is just make a big boxy part that ties in everything where I need it, and then start cutting around that in a way that makes sense for a machining operation. So these 2 holes represent the frame rails that we'll be going through with a 12-inch separation. And these are going to tie into that top X cross beam that I made. And as it stands right now, this part needs to be beefed up a lot. So that's what we're going to be working on. And so I'm just making more bosses here to fill in those weird gaps and add some bracing to that X. And so rather than having a double shear bolt, I'm going to have a threaded hole on each of those corners. And you'll still have double shear mounting on the bolts, but you won't have to have a nut on the end of it. So it reduces part count. And on aluminum parts like this, whenever you have a thread, you just want to make sure that you're using a threaded insert or a helicoil so that the threads don't rip the aluminum out under high torque. So I need these really big bump outs on each of these to make sure that I have enough clearance for the rod ends, which the housing of the rod end is just huge on these upper control arms. It's 3.5 inches in diameter. And that's because they're the biggest rod ends that I could find for an application like this. They're a 2-inch inside diameter and a 2-inch thread, which would be overkill for anything else other than this crazy vehicle. Most of the stuff that I found on the trophy truck suppliers websites goes up to about 1 inch for rod end size, but these are double that because the tires are double anything that's out there. So now I'm starting to get what is looking like a cool shape. I just need to add some lightweighting cuts and some features that are going to make sense for machining and make sense structurally. And it's usually not best practice to add outside radiuses to machine parts because outside radiuses are harder to machine than inside radiuses because the tool can chatter on those outside radiuses as you're cutting them. But for a structural piece like this, you want to reduce any sharp corners because anytime there's a straight edge with a sharp corner, you're going to have a force concentration that's going to increase stress loads on the inside of the part. So radiuses everywhere is the rule of thumb. So now I'm just finalizing these cuts here. And what I like to do is make the cuts first and then add all the fillets afterwards. Because if I need to make any additional cuts or I need reference sketches, it's easier to go off of those straight lines than a part with a really weird compound radius that's going to require a ball end mill operation. And then I'm going to mirror these cuts on the bottom so that the part is equally strong in both directions and as light as possible, or I have at least 3/4 inch wall thickness everywhere, and then adding those fillets in for those draft cut machine operations with the ball end mill. And so the idea here is that I didn't want the tubes to be going through the part. I wanted the part to clamp to the tubes. This part would rest on top of the tubes in the chassis, and then there would be a clamping piece that comes in from the bottom and ties it all together. And it looks like this part is done. Now we can move on to the chassis next.